So in this lecture, we will see about AVR microcontrollers and AVR tools like assembler, compiler, debugger and loader, and design of one AVR microcontroller based system. AVR belongs to RISC family, 8-bit RISC family, is manufactured by Atmel company. Being a single chip microcontroller, most of the peripherals are inbuilt. This is known as a modified Harvard architecture, whereas actual Harvard architecture has separate program memory and separate data memory. However, it is modified Harvard architecture. That means there is only single memory for program as well as data, but it is modified in the sense most of the registers are available for almost all instructions. The memories you have, flash is there, static RAM is there, E square PROM is there. They are available in models like 6-pin ICs, what is called tiny, and 40-pin, more than 40-pin ICs called mega AVR. In both the cases, the data bus is 8-bit. X mega is available in second generation 16-bit microcontrollers. Otherwise, for high computational units, UC3 is a 32-bit AVR controllers are available. So as I said, though we are saying about RISC controller, but the architecture is von Neumann. So that is, there is only one memory for program as well as data. The architecture of AVR microcontrollers is, it has 32 general purpose registers which are of 8-bit. So obviously your arithmetic and logic unit is 8-bit, and on chip it has a static RAM, E square PROM and flash memory, and it has peripherals which are like serial peripherals, timers, A to D converters, analog comparators, input output lines. These 32 registers are mapped into the memory space of the microcontroller. Most of the instructions can be accessed in one cycle itself. Except the last 3 registers, they can be paid as 16-bit registers because they are used for index purpose. The stack pointer is a 32-bit register. So the address of these registers, they are mapped into the memory space, starts from 00 to 1F, whereas out of the 32 registers, last 6 registers can be paid, that is X register, lower byte, X register, higher byte, Y register and Z register. The microcontrollers can be also classified based on the available memory of the flash, E square PROM and static RAM. For example, Atmel 48 has 4K flash and 256 bytes of ROM, 512 bytes of static RAM. But Atmel 328 has 32 kilobytes of flash, 1 kilobytes of E square PROM and 2 kilobytes of static RAM. Generally, the RISC controllers has many clock sources, as can be seen that there is a main crystal oscillator where the clock can be generated, or it can be external oscillator or a low frequency oscillator like 32.767 kilohertz or a RC oscillator. Timers can have external oscillator independently can be connected to the timer modules. These clock sources can be selected with the help of the multiplexer and can be divided by prescaler so that various peripherals will get different clock sources like ADC, flash memory, timers, and so on. There are many peripherals, generally used peripherals, which are integrated in Atmega CPU. Like in Atmega, there are 32 general purpose input output lines where they can be configured as the input or output, individually programmable bidirectional. There are two timers, in some cases three timers. One is 8-bit and other is 16-bit. It has inbuilt real-time counter and PWM channels. It has inbuilt A to D converter up to 8 channels. There are serial ports, asynchronous receiver transmitter. There is serial peripheral interface and I2C serial interface, which is a synchronous communication. There is an analog comparator and watchdog timers. Let us see how a general purpose input output port works. These are each port has 8 lines. They are named as port A, port B, port C, and port D. And you can define the port pin as port A.0, port A.1 to port A.7. Each pin can be configured as an input or output with internal pull-up resistors, and you can configure them as an output or as an input, or you can send the data as a high or low. So the generally used registers while using the ports are, for example, in case of a port A, so this is a 8-bit register where as you can see, every bit represents the corresponding port bit. For example, D0 represents port A.0, D1 represents port A.1. So if you write 0 here, then the data will be 0. If you write 1 here, the data will be 1 for that particular port bit. Say for example, if you want to make port A.7 as a 1, so write 1 here so that that particular bit will be 1. The second register is called configuration register. So this register will decide the direction of the port, whether the port is output or the port is input. If you write 0 here, then port A.0 will become input. If you write 1 here, then port A.0 will become output. If all the bits are 0, then entire port A will be input. If all the bits are 1, then entire port A will become output. So if upper nibble is output, lower nibble is input, then write F0. The other way, write 0F. If alternate bits are inputs, then you can write 0, 1, 0, 1. That means it is AA. So like that, every bit of the port can be individually programmable, whether it is input or output. If you want to read the data from the port pin, then use this register which will read the data from the port pins and store in this register. For example, port A.0 data will be available in this bit D0 bit, then A.1 will be available here. So in general, these are the three registers which are used for every port of the microcontroller. So repeat, data direction register will decide the direction of the port, whether it is output or input. Port A register will decide whether the data is high or low. Pin A register will decide whether whatever is the data on the pins is high or low. That means this is pin A is to read the port, port A is to write the port, DDARA is the configuration, whether the port is output or input. DDRA register we don't change, we initialize in the beginning of the program because the direction of the port is always more or less same. Say for example LED, we initialize always as a output port. Switch, we initialize always as a input port. So we don't need to change every time. But data will be keep on changing while writing or while reading. So we frequently use port A and pin A registers in the program, not DDRA. So this is what is peripherals or SFRs, which you need to be used as a part of the program while initialization. When you actually see the port pins on the microcontroller, as you can see, for example, DIP package, 40 pin DIP package, where port B PB0 to PB7 is available here on pin number 1 to 8. Then PD0 to PD7 is available from pin number 14 to 21. Then port C is available from pin number 22 to 29, and port A is available from 40 to 33. So they are individually programmable, 4 ports, so 4 into 8, 32 input output lines are available. But most of the port pins are also having more than one function, like is given in the bracket. For example, port A also work as a ADC, that is ADC0 to ADC7. Similarly, port B is having timer functions, timer 0, timer 1, analog input 0, analog input 1. Then serial peripheral interface, that is slave select, MOSI, MISO, SCK. Then port D has a function of UART, that is TXT, RXT. And interrupts are there on PD2 and PD3. And PD4, PD5, PD6 are output compare and input capture. Port C has the I2C bus, that is SDA and SCL. And timer clocks can be applied on PC6 and PC7. So the power supply to this controller is VCC is on pin number 10, ground is pin number 11. And for A to D converter, VCC is there on 30, ground is 31, and the reference voltage for ADC is on pin number 32. The reset of this microcontroller is active low, is there on pin number 9. You can connect the crystal on pin number 12 and 13. Now let us see how to choose a microcontroller based on the specifications. If you see the data sheet of any microcontroller, for example, in our case, let us see Atmel 32. Atmel 32 is available in two forms, Atmel 32 and Atmel 32L. So L means low voltage. This is called in-system programmable flash. That means this microcontroller, you can write the program without removing from the target board by using either JTAG or serial peripheral bus. So you don't need a special programmer to program this chip. The futures are like, one is about this is a RISC architecture. Second is most of the instructions are single clock. In one clock cycle it can execute. It has more number of resistors so that it it will be used for faster operations, faster execution. So 32 registers are there. It can work up to 16 megahertz. Fast multiplier, 2 cycle multiplier is there for multiplication operations. Atmega 32 has 32 kilobytes of flash memory and 10,000 times you can erase it. And it has a PROM and first about the boot loader. So in system programmable launch boot program is there, so that with the help of this you can program the flash memory of the microcontroller without using any external programmer. And 2 kilobytes of static RAM is there. JTAG compatibility is there, so that you can interface the JTAG port for debugging through personal computers. There are timers, 8-bit timers and 16-bit timers. Timers has functions like input capture, output compare, and PWM output. It has an inbuilt ADC of 8 channels of 10-bit resolution, and it also has a programmable gain to the channels, and serial ports are there, synchronous port is there, asynchronous port is there, and it can operate up to 2.7 volts if you have a 32 Atmega 32. Otherwise Atmega 32L can operate up to 2.7 volts. Atmega 32 operates from 4.5 volts to 2.5 volts. Operating speed for Atmega 32L is 8 megahertz. Otherwise Atmega 32 can operate up to 16 megahertz. And the power consumption in active mode is 1.1 milliamperes, and ideal mode is less than 1 milliampere. So this is the criteria. Looking at your application, one has to choose the amount of memory, the amount of peripherals, and for signal processing applications, the amount of static RAM and A to D converter, and the number of channels and the conversion time. While mounting, you need to be careful about the package. The packages, different packages are available. Say for example, DIP package has 40 pins, both the sides. The distance between the pins is 100 mils. Whereas the SMD packages like TQFP packages is having all 4 sides pins without holes. There are pads are there, 44 pin IC it is. So package is important. Now let us see how to write a program for this microcontroller. Before that, let me explain you about the board design. You can see the board we have designed, where Atmega 32 microcontroller is there, which is a 40 pin DIP package. So this board we program it by using this connector, what is called in system programming, ISP. So with the help of the USB ASP programmer, we connect it on this 10 pin connector and program the flash memory. So there is a crystal which is mounted, where the operating speed of this microcontroller is decided by this crystal. So all the rest of the applications we are using Atmega 32, operating speed is 8 megahertz. Let us see the design of how to design a microcontroller board. So I was telling about Atmega 32, which is having 4 ports. We have connected the minimum system design, means pin number 10 is connected VCC, 11 is connected to ground, pin number 12 and 13 is connected to a crystal, which is 8 megahertz, and 2 biasing capacitors are there. So that's all. That completes the minimum system design, where the microcontroller will start working. If you want to connect a LED, say for example, as you can be seen, there is a LED is connected on port D, PD7 and one series resistor. So if you design this much circuit, that is microcontroller, power supply, crystal, and if you connect a LED, then you can write a program so that to switch on or switch off the LED to verify your board is working or not. But to program this controller, you require a in-system programming feature, which is there on port B, where you have to connect SCK, MISO, MOSI, and the reset signal to a connector. So we have used a 10-pin connector to connect the computer's USB port to this ISP for programming. So as you can see, port B, PB5, PB6, PB7, reset, ground, and VCC is brought it on this connector, so that through computer's USB port we will connect it here by using USB to ASP converter for programming this chip. So this connector and this power supply and crystal is good enough to program this board. So other part of the design is, if you want to generate, if you want to give the power, either you can give the power through this USB connector 5 volts, so that computer's USB will give the power to this entire board. Say for example, I will highlight this USB connector 5 volts. Now you can see everywhere the 5 volts power supply is highlighted. That means we are giving the entire board power of 5 volts by using this USB connector. So this is one source of power supply. Otherwise, we can connect a 12 volts or 9 volts DC power supply by using this regulator, where it will convert this 12 volts into 5 volts, which is available on this connector. 12 volts power supply we are recommending because this 12 volts power supply is also used for driving the motors. On board there is a L293D driver IC is there, where it can drive either DC motors or stepper motors. There is a relay driver is also there, which requires the 12 volts power supply. So 12 volt supply is required by motor driver and the relay driver. So that is the power regulator design. The microcontroller, apart from there is a LED which is there on D.7, there is a LCD connector is there, where the LCD is connected on port B, PB0 to PB7. PB0, PB1, PB2 is connected to LCDs pin number 456, which is called handshake signals, RS, read oblique write bar, and enable. And we have not used D0 to D3 bits because we want to transfer the data in 4-bit form, not 8-bit. So we are using only 4 data lines, that is PB4 to PB7, where the byte is transferred in nibble by nibble form. The pin number 1 is ground, 2 is VCC, 3 is connected to ground by using resistor. So this will give the power to the LCD. This will adjust the contrast of the LCD. The pin number 15 and 16 is meant for power LED, where the backlit yellow LED is on because of this power supply. So port B in this design is used for interfacing the LCD in 4-bit form. So 16 by 2 or 16 by 4, any text LCD can be interfaced on this connector. If you want to interface the graphics LCD, like 64 by 128 graphics LCD, where you can access pixel by pixel, is also there is a provision on this board, where is a 20-pin connector is used, and the buses used are port A and port C. The reset is active low in this microcontroller. So when this reset pin is, when the switch is not pressed, this reset pin is connected to VCC. When the switch is pressed, this pin is connected to ground, where this point is connected to ground. In order to communicate this microcontroller to the computer or any other serial ports, there are two pins are there for asynchronous communication, PD0 and PD1, TXT and RXT. But since this is works on TTL standard, where the voltage levels are 0 to 5 volts, if you want to connect this port to the computer serial port, then you require this IC called MAX232 driver, which will convert these TTL signals into RS232 form. So on this connector, COM connector, 3-pin connector, the voltage levels are plus 12 and minus 12 volts, so that you can use them for connecting to the computer serial port, which is the RS232 standard. If you want to connect to the Bluetooth or Zigbee, then you don't need this driver IC. Directly, as you can see, PD0 and PD1 directly available on this connector, so that if your Zigbee or Bluetooth is operating 3.3 volts or 5 volts, then you can use this connector. Make sure if your Zigbee or Bluetooth is 3.3 volts, then even these voltages also 3.3 volts. That means your microcontroller regulator IC 7805, you instead of 7805, you connect 1117 IC, so that it will give 3.3 volts power supply to the board. So there is a motor IC driver bridge, which can drive two DC motors or one stepper motor. So port C, PC4, PC5, PC6, PC7 is connected to this motor driver IC. PD7 will enable this IC, so that you can connect two DC motors on S2A and S2B for one motor, S2C and S2D for other motor, or one stepper motor where common voltage is connected on the pin number 1, where 12 volts is available, and S2A, S2B, S2C, S2D is used for interfacing 4 windings of the stepper motor. There is a provision to interface servo motor, where servo motor operates on 5 volts. So the PWM signal you can generate on PD5. You can also interface a graphics LCD, touchscreen TFT LCDs, where it works on serial port, so PD0, PD1, and for reset operation PD2 is provided on this 5-pin connector. If you have any touch screen like resistive screens or capacitive screens which are used in mobile phones, if you want to use it, you can interface on port A, where since anyhow port A has a to D converter, so you can read the data on port A to find the coordinates of the touch screen. Some of the pins are brought it outside, like PD2, PD3, because they're also not only as IO lines, but they're also interrupts INT0 and INT1. So while interfacing any sensors, you can interface here for testing them. Similarly, ADC is brought it outside, that is PA1, PA0, so that if you want to interface any temperature sensors like LM35 or Hall sensor, you can interface for writing the programs. To interface keyboard, the ports are brought it outside, so that port A, port B, port C, port D is available on the connectors. Port A and port B is available on 8x1 connector. Port C and port D is available on 5x2 connector. You can give the power by using this jack of 12 volts DC. There is a real-time clock RTC is there on this board. DS1307 calendar chip is there, which is a SMD IC is mounted. SOIC 8. For this IC, the low frequency crystal Q1 is 32.767 kilohertz. Then the data is used I2C bus port C, PC0, PC1, SCL and SDA of the microcontroller is connected over here to the DS1307 or RTCIC. So that is in short is the design of this Atmega 32 board. The board side, if you see the placement of the components, the LCD connector is here. Mount the LCD towards the board. So the LCD should be inside the board. Pin number 1 is this. You can also mount the graphics LCD here. Port B, port A connectors are here. Port C and port D connectors are available here. 12 volts DC you can give here. Otherwise, by using in-system programming, you can give the power and you can program the board. The relay output is available here. The serial port after RS232 driver, the signals are available here. Without RS232, the serial port signals are available on this here, on this connector for interfacing Bluetooth or Zigbee. Graphics LCD touch screen you can interface here, which requires again a serial port. The keyboard or interrupts you can use on INT0 and INT1 pins. Similarly, A to D converter you can interface other than this 8-pin connector, so that one side VCC, other side is ground, center pin is the input. The board is operating on 8 megahertz right now. You can go up to 16 megahertz by using this crystal. The reset switch is mounted here. A real-time clock RTC DS1307, which is SMD IC, is mounted here. All the resistors and capacitors are surface mounted devices. The package is 1206. The capacitors has a direction, more than 1 microfarad capacitors. Positive side the symbol is printed plus and this is minus. Every capacitor above 1 microfarad there is a direction. Similarly, LEDs can be seen. The anode is here, cathode is here. This is the LED which is connected on port D.7. Similarly, there is a power LED again. Anode is this side. That is long lead should go here, short lead should go here. So that is the direction. While mounting the regulator, the heat sink portion is this where the white band is printed. So that means heat sink should be outside the PCB. The diodes has a direction. This is the cathode. So silver band should come here. So that is the power diode. Crystal doesn't have any direction. Switch, there is no direction. But the connectors has a direction. As you can see the notch, there is a notch, there is a notch. So you must strictly put this 5x2 connector in the direction only. These connectors, that is burge strip, there is no direction, but smaller portion should go inside the PCB, long lead should be outside. ICs has direction, there is a notch, that means this is pin number 1. There is a notch, this is pin number 1. There is a notch, this is pin number 1. Similarly, this DS1307, there is a notch, that means this is pin number 1. Transistor as a direction, flat side portion should come this side. So this is as far as the mounting of the components are concerned. There is a variable resistor here where it is has no direction. In any direction you can mount it. Okay, now let us see how to write a program by using assembly language. In your folder, there is a software folder where AVR tools software is there, which is a assembler from the Atmel company. So you can use this wave rasm.exe. So then this editor window will be open. Let us open a example. Go to application notes. In application notes, first let us see at least one example. The example name is called ass1.asm. So in this example, first we have to include the name of the microcontroller which you want to use, so that in this include file all the registers of the CPU is defined. Then in the program, first we are initializing the stack pointer. Stack pointer is R16 low and R16 high represents the stack pointer. So the highest available internal RAM space is initialized with the help of this syntax that is called RAM end to the stack pointer. Now hardware initialization. So hardware initialization means, first if we want to use data direction register D, then we are loading FF into R16 register, then we are moving R16 register contents into the data direction register D, so that this port will become entire port data port D will become output port. Every port has is a set of 3 registers. So for port A it is called port A pin A DDR-A. For port B it is called port A pin B DDR-B. Port C it is called port C pin C DDR-C. For port D it is called port D pin D DDR-D. So since in this example we want to set or clear the bit of the port D.7, so in the main program in assembly language we are saying set a bit port D.7, so that D.7 bit will be 1. Then we are calling some delay. Then CBI clear bit port D.7, then call delay relative jump to again. So this will be in the infinite loop, so that D.7 bit will be set and clear. In the delay we have initialized some count, and then we are decrementing that count, and branch if not equal in the loop again decrement some another register, so it will be repeated. Once the all the registers becomes 0, then return from the function. So this is just one example of how to write a assembly language program for the AVR microcontrollers. So once the program is done, then you can go and say assemble the program. As you can see, it should say no errors. That means your program doesn't have any syntax errors. Syntax errors means, say for example, if I don't give some a comma here, and if I say assemble, then as you can see the error, there is a one error is there in line number 23. So you can go to the main program. If you double click on the error, directly as you can see in the line number 23, it is indicating it is that there is a error. So you have to at least first remove the syntax errors by using the assembler. Then how to simulate this program? Say for example, if you do not have the hardware, then if you want to verify whether this program is working or not, then the Atmel company provides a studio, AVR studio, to debug the programs through simulations. So I'm using AVR Studio 4 for testing purpose. So as you can see, AVR Studio 4. So when you start the AVR Studio 4, say open, then whichever is the example you want to open. Say for example, in our case, the example is there in software folder, AVR tools, application notes. So ass1.obj file. Say open. Now this time it is asking to create the project file. So just say save. Yes. Okay. Now the third step is it will ask for the simulator, which simulator you want to use. So AVR simulator, and which microcontroller you want to simulate. So select the same device which you have written the program for, that is 90S8535. Say finish. Okay, now you are supposed to give the path where your uh, assembly language program is there. So that is not system32, it is in your folder where you have created. So in the same folder where your examples are there, that is in software folder, you have AVR tools. In that, give the path for the application nodes. So in the folder, this finally it should be AVR tools and the application nodes, because that is where your .asm file is there. Okay. Now you will see that on left side the CPU registers are open, right side CPU peripherals are open, and your assembly language is displayed over here with the cursor highlighted. So if you miss any one of these steps, then the screen will be blank. And the register windows. On right side it will show the CPU peripherals like ports, timers, ADC, and the UART. So as like any debugger, you have the features like run, which will run the entire program. You can stop your debugger. You can reset the microcontroller, that is program. Then you can do single stepping, step into, step over, step out, so that whenever you have some functions, you can either execute the function, you can come out of the function, you can run up to the cursor. You can do auto stepping, so that step by step it will execute and show the results. So one should, these are the standard debug tools where one can verify while tracing the program. Okay, so now currently the cursor is on the first instruction. If I execute the program by single stepping like F11, so as you can see R16 contents are modified. So if I execute by single stepping, SPI port D.7, so I want to see port D. Now DDR-D is loaded with FF, that's what we have executed. Now the port register, this if I execute one more instruction, now you can see the value is loaded 80. Now you can see the contents are shown here. So, or you can execute the whole program by single stepping. Now as you can see, the bit is getting modified based on the program, because since there is a huge delay, so it takes some time to complete this function. So or you can reduce the delay and quickly you can see the effect on the bits. So one can write the program in assembly language by using assembler of the Atmel company, and you can use the AVR Studio to simulate the program and to view the peripherals of the how the data is getting modified on the port bits. So this is just to demonstrate how one can work with the assembly language programs. The same program we can also load it on the board. So as you can see, there is a board, there is a LED, which is a LED which is as I have discussed in the circuit diagram. The LED is connected on port D.7. So I will connect this ISP to the computer's serial port. So this ISP I will connect it by using the programmer called this USB ASP programmer, where this side I will connect it to the computer's USB port, and this side I will connect it to the board where USB connector is there. So this is where you will have to connect it. Now if I connect it to the USB of the PC, now the as you can see, the the board is powered up by where the LED is indicating that the board is getting 5 volts power supply. Now I want to program this controller, whatever is the assembly language program you have written. So there is a software called Sinaprog. So let us see how to program the AVR microcontroller board. So we are using this programmer, USB ASP programmer, to program the controller. So when you connect this program to your personal computer, you can go to the control panel. In control panel, in device manager, when you select the device manager, so if you connect this programmer, so now if you see the connect the USB to the computer USB port, you will notice that it shows that libusb-win32 device USB ASP is installed. So this indicates that the computer has recognized your programmer and the driver is installed. If this is not there, then if there is a exclamation is there, then you will have to right click on that, then go to update driver software. Then you have to give the path where that folder is there, where the drivers are there. See, the drivers are there. You have to give the path of in your software folder, USB ASP 2009 folder. In bin, there is a win driver is there. So give the path of this folder libusb underscore 0.1.12.1. So if you give the path, then the PC will automatically install the driver for the USB ASP programmer. If the operating system is Windows 7 or Windows 8, then if it is a 64-bit operating system, then you download the appropriate version, and specifically in Windows 8 you need to change the PC settings. So go to settings, in PC settings, in advanced startup options, in troubleshoot, in advanced options, there startup settings, you have to disable driver signature enforcement. So this is what security you have to disable, and then restart. Then it will automatically next time will install the driver for that. Pro. So this software, where first you say after connecting the programmer, press search button, then this should say the programmer is detected. Otherwise, some problem is there on your board. Okay. So now it is saying searching is okay. So if this is not saying searching is okay, that means there is a problem either on the board or on the programmer. So never use this advanced feature, because in advanced feature there are some bits which are called fuse bits. These fuse bits decides the operating speed, operating clock, security bits of the microcontroller. Usually in case of Atmega 32, we say 3F, DF, FF, these bits, so that external crystal is selected. You can always refer the data sheet about these fuse bits. If you are not aware of it, then don't modify this bit, just simply close it. So you only just has to say search, so that it should say search is okay. Now you go to your browser and select the program hexa file. In application notes, you have written a hexa, you have created a hexa file of ass1.asm. So say save. Now you say program. Once you have programmed, now you can see on your board the LED is blinking. So these are the basic three steps. First, go to assembler, modify the program, increase or decrease the delay. Say for example, instead of 08, I will make it 02. So now I made some changes. Now you should say assemble. Say yes. Now the assembly is done. No errors are there. Now if you want to simulate it, you can simulate the program again if you want. There in that case, what you will have to do is you will have to stop it, break it. Now it says that the program is getting modified. Right now we have 08, but if you say yes, then now see the new object file is loaded with 02. So that is updated file is loaded here. So again you can simulate if you want by say auto step. Now this time you can see the delay is fast, is because the count is small. Or if you are not interested in simulation, then directly go to the Sinaprog software. Again you can say search, it's ready for programming. Go to your folder, select that file and say save, and now say program the flash, not e square prom, program the flash. If you say program the flash, now you can see now this time it is blinking very fast. So these are the basic three steps of testing and debugging and real-time verification on the board. Okay, now let us see how to write a embedded C program for the AVR microcontrollers. So there are two softwares are available. One is CodeVision AVR, other is WinAVR, which is open source. We are starting with CodeVision AVR because it has some good features where even the beginner can write the program for the controller without knowing about the hardware initialization or the control words. That is, there is a feature called Code Wizard that we will see. So basically, you need to install the CodeVision software. After installation, if you start this CodeVision AVR, so this will be the window. You can close these right side windows. Okay, even function call tree also you can close. Code information. Okay, you can keep two windows open. One is code navigator, other is the code itself. There is a very good help is there. You can go to help in help topics. If you see the help topics, first is about the integrated development environment. So for example, how to work with the projects, how to create a project, and there is a step-by-step procedure is given, or how to open an existing project, or how to work with the files, how to create a new file, or how to open a existing file. Is at least one should know how to create the files and the projects. There are libraries are there. You must everybody should know about library functions in CodeVision. About say for example about the standard input output functions or the delay functions or some mathematical operations. So whenever say for example if you see the delay function, so the syntax is given how to write a delay in milliseconds, how to write the delay in microseconds. Whenever you are using this delay function, you must include the header file called delay.h. So this is, you should say hash include and the name of the header file. So at least one should spend half an hour time in knowing about various functions and how to invoke those functions in the CodeVision C compiler. The procedure for creating a project is there are two methods. One is go to file, say new, then we want to first create the project, so select the project, then say okay. Now it is asking, do you want to use the code wizard? Code wizard means now this will create the initial template for you for the C program, which consists of the hardware initialization. Just to begin with, let us not use the code wizard. We will create a project. Say no. So now it is asking give the name of the project file. So I will give name, say YSR. You can see the extension of the project is always .prj file. So save. It has saved in C folder CVAVR bin. Now the next step is, do you want to add any files? Means you should write your own C programs and add them here. But right now you have not written any C programs, so there is nothing to add. Similarly, output directories, you can see whenever you compile your program, so where the exe file, object file, list files will be saved, you can always give the path. Otherwise, by default, whichever is the folder you have selected, in that exe folder, object folder, list files, it will create these output files. About the C compiler, now you need to set the model of the program. Say for example, first of all, which microcontroller you are using. Say select, say for example, Atmega 13, Atmega 32. Then what is the operating speed? So on our board, the crystal which we have connected is 8 megahertz. So we must always use the 8 megahertz crystal. So crystal is 8 megahertz. Then it is asking the memory model. So for a compiler, you should know what do you mean by memory models. Say for example, your stack size is 512 bytes, heap size is 0, total internal RAM size is 2048. So when you choose the environment, you need to be careful about the optimization for size, optimization for speed, or you want more stack size, you want or more RAM size. So finally, whatever is the available space is there, one has to carefully configure how much memory is allocated for which purpose. Okay, so then you can say okay. Now your project is created. The name of the project is whatever the name you have given is created. But then now you will have to write a C program. So for C program, you can say new. Then now this time you want to create a source file, which is a C file. Say okay. Now you can start typing the program. Say for example, include and so on. So after typing, you save your file, and the extension should be, say for example, 123.c is saved. But when you save this file, you can notice this is coming under other file. So always remember, whenever you write a C file, the C file should not be in other files. It should be part of your project file. So for that, what you should do is you go to project and say configure. In configure, now you select your project file and you must add. So which C file you want to add, 123 you want to add, say open and OK. So now if you see this 123 is part of your project file. So that means now whatever you are compiling is compiling for that project. This is the normal mistake students does, where the C files they put it in the other files. So that means this will never be compiled. Whatever is compiling is happening because the file which is included here. So this is how one can create the project, and one can create a C file and add as a project file. And once you compile it, it will create a hexa file. Let me type a small program so that we will see how to compile that. So all the example programs are there in sample programs. Say for example, first program, which is a C program we want. Okay, so this I will try to put it in my newly created Now you can see even the color is also changed. Okay, now after typing your program, the next step is there is a tool called built all project files. When you compile it, it should say no errors and the hexa file is created, and it will also show you how much memory is occupied while creating this file. Okay, so this is the resources which it has occupied. Now the compilation is done and your output file is stored in this folder, your project folder, wherever you have created. So this output file, that is 123.hexa file, whatever you have created, that we want to burn it on the chip. But if you want to simulate it, so since you have installed this code division first time, go to settings, and in debugger you select the debugger name. So the debugger is the same thing what you have installed, that is in the your software folder. There is a tool called AVR Studio 4. If you install this software, then this will recognize this folder will be created in C program files, Atmel. In AVR Studio 4, you will find in AVR Studio 4 this AVR Studio.exe file. Say open. So now you have set the directory path for the AVR Studio 4. If you say OK, now if you say OK, now next time you don't need to set the path because the compiler is installed, studio is installed. Just if you want to start simulation, as you can see, run the debugger. So this icon you will have to select. Now see, the AVR Studio 4 is automatically opened because you have set the path. Now you can say open wherever your project you have saved. Right now we have saved in C folder CVAVR. In that you have created in bin folder. As you can see, your project is created bin folder ysr dot. The debugger always require cof file, cof, always. Your project extension should be cof file. If you say open, now do you want, it will is asking name of the project file for the studio. So .aps file it will save in that folder. Now the next step is you want to use the simulator. Procedure is same what I explained in the assembler, and which microcontroller you want to simulate. So you want to simulate Atmel 32. So you must select the correct controller while simulating, otherwise it will throw error. Atmel 32. Say finish. Now you can see the left side same environment, that is the CPU and its register. Right side is the peripherals and its resistors. So the program is same like assembly language, where D.7 we want to make it output port, and then set the bit, clear the bit by using C program. Okay, so if you want to simulate it, you can do the single stepping, where you can see step in. Now you can see in data direction register the bit is modified. Now in port D.7, right now in port D everything is 0. If I do a step, now as you can see port D.7 is set. If you want to run the whole program, then you say auto stepping. So if you say auto step, the whole program will be start executing. Since the delay is too large, it takes a lot of time. So I will reduce the delay. So what you can do is you can go to your toolbox and you say break. Send, and after break, what we do is we go to our main program. In the main program, I will reduce the delay to, instead of 1000, I will make it 10. Now whenever you make the changes, compile the program and then go to debugger. Now when you say reset, now it recognizes that the program is modified. Say yes, then it will load the modified program. As you can see, now the 10 value is loaded here. Again, if you instead of that, I will run in auto stepping. If I am running the auto stepping, now you can see how quickly the contents of the port D setting and clearing as per the program. So this is how one can use the debugger to simulate the C programs. Earlier we have done assembly language. Now we have done C program simulation, embedded C program simulation. So henceforth we won't be using simulator. We will be directly using the our hardware, that is this, to program it. So let us see how to program the same program. So I will stop the simulation. So there is a stop button is there, break, and I will close the AVR Studio. Okay. So since my compilation is done, I will use the Sinaprog to load that program. So first say search. Now search is okay. Then go to your folder. Right now we have created in C CBAVR in bin folder. That so now it will be there in exe folder. So the extension is always hexa file whenever you want to load it to the target device. Say save. Okay. Now you want to program the flash memory. Say program. Now the flash memory is programmed. Now if you see your hardware, now it is programmed, but then the LED is continuously on. It is not blinking. The reason is, if you look at your program, you have given very less delay, just 10 milliseconds. So you are unable to differentiate between on time and off time. I will slightly increase the delay to, let us say, 100 milliseconds on time and 100 milliseconds off time. So again compile the program and go to Sinaprog and search, and since anyhow already path is selected, simply say program. Now it is programmed. Now if you see your hardware, then that LED which is connected on port D.7 is, the flickering rate is changed. So about the program is very simple. Whenever you create a C file, first you must include the which microcontroller you are using, because all the register names are defined in the header file. And in the main program, we should start always with void main. Void is because there is no return values. And then since we are using in our LED is connected on port D PD7, if you see your PD7, it is connected here. So this bit we want to make it high. So in the C program, we made it DDR D.7 is 0x. So 0x means hexa value 1. Then while 1 means infinite loop. In infinite loop, we said port D.7 because this is the output. This is what I explained. Whenever you want to send any data, then you will have to write it into this register, port register. So this is for configuration and this is for writing the data. So in the program, we said port D.7 is 1, then delay, and then port D.7 is 0, then delay. So this is on delay, this is off delay. Since you are using a delay function, you must include a delay.h. Say for example, I will comment delay.h. Now if you compile your program, so you will find two errors are there. The errors are nothing but undefined delay is shown. So this is not recognized. So whenever you use any functions, the corresponding header files must be specified. So one should include the corresponding header file based on the functions which you are using. Okay, so this is the procedure. Whenever you want to create a project, you can go to file and then you can always say that new and project, and once that is done, then create a new and C file and then add the C file to the main project by using in the project configure folder, where you can configure, you can add the files here and then say add. So then it will automatically recognize here. And you can always configure your project also in project uh, project configuration, at any point of time, if you want to change the stack size, or you want to change or increase or decrease the RAM size, then in the compiler you can always increase or decrease the size of the memory. But then finally whatever is the memory is there, in that only either you can increase or decrease. That is the only you have to play with the available memory space, or then you will have to change the chip itself. So this is one way of creating the project. Second method of creating the project is, there is a code wizard, as you can see, run the code wizard AVR automatic program generator. So if you use this code wizard, now this is asking for which microcontroller you want to create the project. So we are using the first option, not the second. Second is a different controller. So okay. So then it will give you very nice GUI. That is the reason why we are using code vision, where the hardware configuration it will ask. Say for example, hardware configuration means which microcontroller you are using, and what are the peripherals, and then which features you want. For example, the first step one has to choose is which chip you want to use. Say, no, obviously there you can see there are hundreds of chips are there. So since we are using Atmega 32 on our board, so we are using Atmega 32, then we must select the that particular device only. So this is our Atmega 32 here. Okay. Then operating speed is 8 megahertz. Always select 8 megahertz. Now see how many peripherals are there. Whatever is this microcontroller has peripherals, all are shown here. Just to begin with, let us use the ports. Go to ports. Now you can see port A, port B, port C, and port D. Now every port, you can see there are 8 bits are there. If I want to use port D, let us say in port D, last bit I want to make it as a output, because there we have connected a LED. So make it this bit as a output. That's all. So we do not want to use any other peripherals at this point of stage. Go to program and say generate, save, and exit. Now this option will give us a template for C program. So if I say generate, save, and exit, now it will create one project as well as the C file, so that whatever is the minimum required program is there will be automatically created, so that you don't need to worry about hardware initialization. You don't need to worry about how to calculate the control words for your hardware initialization. Otherwise, you have to manually calculate and specify in the program. So that is the advantage of using this code wizard AVR, which is a unique feature in this compiler. Otherwise, if you are using WinAVR, more or less the program is same, but this code wizard option is not available. So now it is asking the name of the C example. So you will have to give this name 3 times. Say for example, if I say A, now if I say A and save, now 3 times it will ask. Give the same name 3 times for just to remember easily. So third time also, if you give A as a project name, one for C file. Now you will see that your project is created A dot project, A dot C. In A dot C, you can see this blue is the comments. Otherwise, whichever is the controller you have selected in Win Code Wizard, that particular header file is included. Main is there. Now you can see the whatever is the hardware initialization is required, that is done. Like say port, say for example in data direction register, we said DDRD D.7 we want to make it active high, so that is why 80 is automatically done. Whichever is the registers we have not selected, then that is all initialized with 00. So this is one way of creating your own template. Otherwise, if I delete all the comments, you will see that actual code is only this much. This is the minimum code where you can, so either you can use in code wizard and initialize the hardware of the microcontroller, or if you doesn't want code code vision compiler to create any hardware initialization, then you can go to file and create new project on your own. So these are the two methods of writing your own programs in code vision and compiling the programs, and loading the programs we are doing by using Sinaprog software.